Okay, this is example 15.15. I recommend you look at 15.14 also. It's a really cool problem. Okay, this one has a disk and it is on a smooth surface. It's attached to an elastic cord, so it's not a spring but a cord, and has a stiffness of 20 newtons per meter. It's unstretched in this state right here. Okay, it gives us the fact that it has some initial velocity, and that velocity is perpendicular to this 0.5 meters in the y direction that they give us right here. Okay, what else we got? Determine the rate at which the cord is being stretched by the disk whenever the cord gets stretched 0.2. So we got to think about what's going on, right? If this did not stretch, it would make a nice circular path where this was also 0.5 meters. But it's got some stretchability to it, so that path is actually going to get longer and longer until some equilibrium point, which we're not at yet. So they want us to know when this stretch is 0.2 meters. So this initial velocity, we'll call it v at 1, is going to have some components to it, right? And the velocity is always tangent to the path, so I'm going to draw my velocity vector, and I'm going to call this one our velocity at 2. Alright, we also have a radial component. This is how much it is stretching, or the rate of change at which it is stretching, and that's going to be out from our radial direction, like so. Okay, and let's call that v double prime at 2. There is also going to be some component in the transverse direction like this, and should make that a little longer actually. So that when you add these vectors together, you get our vector v. Okay, so I'm going to call this one right here v prime. And what we have then is a triangle v with a radial component v double prime and then v prime. Okay, and the reason this is important is because when we conserve momentum, it's talking about the perpendicular speed, and that's going to be v prime right here. And when we conserve energy, we're going to be talking about this component, because conserving energy only cares about speed. We can't be particular with components when we conserve energy and look at kinetic energy. Sorry. And from two pieces of a triangle, we can find the third piece of the triangle. Alright, so let's get started. And I'm going to conserve angular momentum first. So I'm going to say h about O, it's our origin, at 1 is equal to some h about the origin and some final state 2. Let's break it down into components, because we're going to be looking at that prime, this one right here, the prime component. So let's look at the radius in the initial state, the mass of the disk times, v prime at 1. and that's going to equal some R2 times the mass of the disk and some V prime at 2. So we're given V prime at 1. That is this perpendicular speed they gave us, 1.5 meters per second. We know the radius initially is 0.5. We know the radius in its final stretched state, they told us, is 0.5 meters plus 0.2 meters. And we can cancel the mass because the mass doesn't change and solve for V at 2, V prime at 2. And I'll get 1.071 meters per second. And we'll hold on to that. Okay, so that was conserving angular momentum. Let's conserve energy now. Let's do a little T1 plus V1 is equal to T2 plus V2. Okay, well, does it have some motion energy, some kinetic energy? It does. It's got some initial 1/2 mv at 1 squared. It says the spring or the elastic cord is unstretched in its initial state. We could still write it since we're dealing with a spring and cross it out just to keep track of it. It is going to have some final kinetic energy, 1/2 mv at 2 squared. And remember our vector, we have the component that's going perpendicular to the arm. We have our vector v, and then we have the radial component. The one we're looking for right now is the one that's the magnitude, so that's our v. Okay, and we're also going to have some 1/2 k x2 squared term because the elastic cord is going to stretch a little bit. We have everything except for this, and so we can solve for it. V at 2 is equal to 1.36 meters per second. Alright, we're not done just because we got to take that triangle. This is our velocity. We had these other components. So this is V. We also had V prime and V double prime. Well, we know what those are now. We have the magnitude, that was the speed we just calculated right there. We figured out how much it was stretching, or how much it was moving in the prime direction using the conservation of angular momentum. All we've got to do is Pythagorean theorem, and we can find out the velocity at which the disk is extending in the radial direction or at which it is being stretched, and that's what they asked for. So V double prime at 2 would be the square root of V at 2 squared minus V prime at 2 squared. And crank the numbers, we can get that it extends at 0.838 meters per second. Take a look at 15.14 also. It uses the similar methods, conservation of angular momentum and conservation of energy. I think it uses work energy actually. But still same kind of thing where we have to break up the velocity vector into its components to solve it.